Hello, Christian.
Either should.
How's the talk coming up? How is the talk coming up?
It's good, I think. Yeah. Yeah.
So when do you think you will have a draft for me?
Yeah. So I haven't changed much in the draft. I went through more of what I was gonna say. The PowerPoint that I sent you, I changed, like made a couple of little corrections to it, but I think that I'll go with that because, well, I mean, for now at least, I want to get the talk down since it's just a week now. But
is it like easier? What is the other thing called? Beamer ready?
The Beamer's not ready yet. No, I haven't had time to get that one ready.
When will you be able to give me a live talk with the Beamer?
I'm not 100% sure. I have a lot. I was thinking I would just stick with the PowerPoint one because I made it look pretty much like what the Beamer would look like.
That is also okay.
And it has animations, so it's pretty. I think that it's what I want it to be as far as the presentation goes. So if I made the Beamer, it would be identical to it, and I have.
So that's okay. Like PowerPoint is good enough, but will you have it ready for a talk sometime? Let's say.
Yeah, I mean
tomorrow or Sunday or something.
Yeah, my mom is actually coming this weekend to stay with me, so she will leave Sunday morning, and then I can give it to you on probably on Monday.
Okay, so Monday can we fix it? Like let's say 4 o'clock.
Yes.
Monday 4 o'clock. Sounds good.
Yep, that will work. Yeah.
And try to get a final version at the time so that that should be the final. Okay.
Yes. Yeah.
As much as possible.
Yeah. I have most of it written out, what I want to say at least. That's what I kind of spent some time on in the past couple of days instead of redoing in Beamer.
Yeah. I really want to see the final one so that I can make corrections.
Okay.
That's why I'm insisting. Okay. Borden? Where is Borden? Oh, Borden is also. Oh, okay.
Yeah, I have to go work at the Elks afterwards. We had somebody call in today, so.
Sure. Yeah, no problem. Another way of looking at it is that hopefully this is the last leg of this whole thing. So use the online version. Hopefully it doesn't stay on. I heard the university is planning for a face-to-face. The university is planning to have a face-to-face semester in fall. That's what they're planning for. So that sounds. But of course, it assumes that everything is going to be well. Yeah. Okay. So, any comments or questions in general? Okay. Jeremy, nice to see you. Yeah.
Hey.
Okay, so we have homework 5 due on Monday. And your midterm 2 to March 26th. Okay, we were talking about a circular wire and we got the vector potential for a circular wire. So now let's see, we can make get some insight of this, and you have to do similar thing for the magnetic field. So this is circular wire still, so hopefully we can wind this up to a certain extent. We can talk a lot more on this, but I think we should stop at some point. Okay, so there is this circular wire, current carrying wire. So there's a current I, and we have the z-axis along the axis of the wire itself. And if we have an observation point anywhere around the wire, it's a vector r, and the length of this vector is r. Let's say the radius of this circular loop is a, and we can also say that's your rho. So this whole thing is rho because of the cylindrical coordinates, and that's your z. So we'll use all this. So it's written in a mixed coordinates often, since it has cylindrical symmetry. So it is good to have rho and z to represent the observation points. And we showed that, remember, magnetic field for a circular wire is given in terms of the vector potential. And usually derivatives are just a matter of working it out. It might be very tedious, but still it's all possible to do. It never you never get stuck on it like integrals. Integrals often are not doable. So once you could know the vector potential, magnetic field are pretty much known, at least in general. So vector potential is that we calculate it in exact form in terms of elliptic integrals, and this was given as phi hat. Phi hat is in the same tangent direction to your r, right? So make a circle with the axis as the center at the point r, and phi hat is tangent to that circle. And the vector potential is given as mu dot over 4 pi, and we used 4a pi, and we showed that this is equal to how much? So this was z square plus a plus rho plus a square. That was a parameter. We wrote it as r square plus rho square plus 2a rho, but radial square is rho square plus z square, so you can rewrite in that form. And we had more terms, right? That's where the elliptic integrals showed up, and this was equal to, what was this? This is 2 over k square, if I remember correct. And there was k of k. So notice this is the argument vector k, or not k, vector, it's a parameter, minus e of k. Am I still in the board space? Yeah, I can probably squeeze this in. And minus k of k, where k square was equal to 4a rho divided by the same quantity. Right, so that was our complete expression for the vector potential. And notice that this is a little not very intuitive, doesn't give you too much insight because these functions are given as integrals. So it's sometimes useful to, at some cost, can we get a feel for this? So let's talk about the situation when k square is small. K square, notice is a dimensionless parameter. So let's say k square is small. And what does that mean? So this is your loop. So earlier we have talked about far field approximation, but this is a different approximation in the sense that there's a curve here. So this region here, so that's k square less than 1 inside here. So if if your experimental setup is pretty much on the axis of or very close to the axis of the loop, then this works out well. And in fact, you can even go farther if you want, as far as you go a little higher from the loop. So that's a very convenient approximation to have. And that is possible to do because now notice these are elliptic integrals. We define them as integrals, but like sine function and cosine function, the most convenient way to use them is as a power series. Like sine function, whenever you want to use this in some of the descriptions, just expand it as a series. Similarly, k and e have expansions. So let's write them down. So the elliptic integrals k and e, both of them have expansions around for large. When this k is small, it is the leading order terms that are important. They both start from pi over 2. So when k is equal to 0, it is exactly equal to pi over 2 and they're identical. And the series begins as 1. And for 1, this is k square over 4. Other one is minus k square over 4. I think that's what it is. Let me check. Yes, one is plus and minus. And the next term differs. That's plus 9 over 64, k raised to 4. And there are higher terms, higher order terms. The next one will be k raised to 6 and so on. And for e, this is minus 3 over 64. And in fact, there is a pattern in this whole series, which shows up in your homework, but we only need this explicit term. So I won't worry about the pattern here. This can be summed up as a whole and summed up as a whole or at least you can identify the nth term as far as pattern looks. So let's get this, let's see if we can find out what this is in the leading order. Like we want to say k square less than 1, that means to say k is small. So we can keep to say, let's say the easiest would be if you can just live with the first term or the next term. So whatever is the leading term that contributes, that's what we will keep. So let's call this whole bracketed term just bracket, let's say. Let's just, for lack of being creative with a variable there, so let me call that just this. Okay. So that's equal to, I have 2 over k square. Let me begin by saying that I will keep only to the constant term. I won't even keep k square. So I can neglect anything that does not have that is up to a k, like even k square I'll neglect. Like that means I want to keep only 1 and a 1 here. But I should be careful. Notice this is 2 over k square times k of k minus of e of k minus of k of k. one should be very careful. Notice that if I drop a higher order in one place, I have to drop it every place. I cannot keep it partially here and partially there, right? Then you're missing things and it will lead to an error. So notice there is a k-square in the denominator. So if there is a k-square in the denominator, and if I want to keep the constant terms, I have to have a k-square plus the next term, right? So I have to at least keep this to k-square, because otherwise there will be 1 over k-square there. So I don't have a choice here. I have to go to the second one. I cannot just blindly keep 1, because then that will be 1 over k-square that will dominate. So let me keep that. So that's k is, and there is a pi by 2, right? So let me say, so this is pi by 2 plus pi by 8 k raised to 4 minus pi by 2 minus pi over, so minus and a minus makes it plus, right? So that's plus pi over 8 k raised to 4. Again, notice why I kept until k, sorry, k square, right? So this is k square. Where? K square, right? I did not want to stop here, because then I will be dropping this k square, and the k square cancels out, so that won't be okay. So I went extra bit there, so I did the extra 1. That's minus k of k, which is equal to, k is pi by 2 plus pi over 8 k squared. Okay. Any questions at that stage? Okay, if that is the case, then these two immediately cancel out. And whatever is remaining is a k square. So that's equal to 2 over k square times pi over 8 plus pi over 8, that's pi over 4 k square. What am I missing here, since I have dropped k4 here? K4 over k square, that's plus order k square I'm missing here. I've dropped a lot of things with k square in here, because the next term was k raised to 4. K raised to 4 divided by k square is k square itself, and that leads to something like this. So the next term here is minus of pi by 2 and minus pi by 8 k square. But there is no point in keeping this, because I have dropped this anyway. Since I've dropped this, forget this. Like, it is meaningless to keep that, because I have missed something else. So drop that. That gives you 1 by 2. So that's pi by 2. Cancellations happen. Minus pi by 2 plus order k squared. Great. Which is 0, right? So what we learn is that, oops, we cancel everything. So up to, if you had to drop k square terms, actually there is nothing left. So that means that the leading term is in k square. So we have to go further down. So we dropped k raised to 4 terms there. So we have to actually keep them, because otherwise we get a 0. And this was what we observed long ago, some 1 week or 2 weeks back, when we tried to calculate the vector potential on the axis. The A does come out to be 0. And that is that signature there, that there is unless you go to k square, this is actually equal to 0. So you have to go further down. So let's do that, right? So now we have the till k4. So let's do that. Any questions at this stage? Okay, so if we proceed, then we repeat this calculation now, just that we go further down. So this is, again, let me use that square bracket, not a good notation, but that's equal to 2 over k square. And hopefully the k4, if we keep the k square terms, that will contribute. 2 over k square, and we have k, which is pi by 2 plus pi by 8 k square, and this time I keep the next one, plus 9 over 64 k raised to 4. And subtract things out, so that's minus pi by 2, minus and minus is plus pi by 8 k square, and this is again plus, this is wrong, right? Pi over 8, so this is 9 pi over 128, right? I have to multiply that pi over 2 in there. So pi over 2, pi over 8 is okay, and the next one is plus 3 pi over 128 k raised to 4. And what am I neglecting? Order k raised to 6, right? So let me just say this is order 6. That means that order k raised to 6. And the next term is minus k. K is simply whatever I wrote here, right? Pi by 2 plus pi by 8 k square plus order k raised to 4 I can actually drop, because anyway I know that when this kills that k square, I'll be left with only k raised to 4. So I won't write that and simply say that I'm dropping order 4. Notice here I'm dropping order 6, and here it is okay to drop till order 4, because in this there is a 1 over k square there, which due to that reason I had to go to a higher order. Okay, what is that all equal to? There will be cancellation as we expect, because earlier when things went to 0, right? All those terms are still here. So that's minus pi by 2 plus pi by 2 goes away. And what we're left out with is pi by 8 and a pi by 8. That's a pi over 4, which makes it a pi over 2 when I get that 2. So this is pi over 2, and a k square is also cancels out of that. So that's also taken care of. All that gives you just pi over 2, which will cancel this, we know. What next? The next one is 9 pi plus 3 pi, that's 12 pi. So that's 24 pi over 128. And that's k raised to 4, but that's only k square, right? After you multiply this down. That's that. And from here, I have minus pi by 2 and minus pi over 8 k square plus order 4, like order k raised to 4. Let me write that down. As we saw before, anything in the leading order cancels out, or leading means the without k square terms that cancels out to 0. But now hopefully we can capture this. How much is this? 20 into 6 is 120. How much is this? Well, is there a factor here going? 24 into, that's 96, correct? I guess. No. Okay, let's go slow. So 8 into how much is 128? So 8 into 10 is 40. So 8 into 10 is 80, and 8 into 5 is 40, so 16, right? So I have to multiply by 16 here, and a 16 in the denominator. Is that correct? Yeah. So 24 minus 16 gives me 8 pi over 8 into 16 k square. That's equal to pi over 16 k square plus order k raised to 4. Okay. Notice you have to do a very similar thing for the magnetic field. I'm doing this for the vector potential. You have to do this in your homework for the magnetic field. So you start from the expression and make sure that you keep the same order everywhere. That's the only important dropping. With a little practice, you learn that, oh, you shouldn't drop things over. Okay, so now we know for k square very much less than 1, which is applicable for regions close to the axis of the circle. We know that the vector potential is equal to phi hat times mu naught over 4 pi times 4ai over z square plus rho plus a the whole square. And is this still in the visible board? Oh no. Let me pin my video. Okay, why doesn't this work? Pin, yeah, pin. Okay. Okay, so then I was saying, yeah. So let's so that's your expression if you want, and we also have a k square, right? Phi square times k square. That's what leads to. So that's pi square, no, pi over 16 times k square, which is 4a rho over the same quantity. But this time not a square. Okay, so I can collect things together, right? So let's do this. Pi a square, 4 cancels out, 4 cancels out, right? So there's a 4, and a 16. So what I'm left out with is pi hat mu naught over 4 pi. Let's stay there. And there's a pi a square times pi, which is good because current times area, right? That's the magnetic moment associated with the loop of wire. And there is still a rho remaining, right? Pi a square times rho. So that's a parameter, that's a cylindrical coordinate. And we have denominator equal to c square plus rho plus a whole square times 3 by 2. The z and rho, that's the two quantities that changes as you move the observation point. And if you're very close, that's of course the vector potential. And you see that if you set rho equal to 0, it goes to 0. Right? That's what we experienced earlier. That this does go away to 0. Let's calculate the magnetic field using this smaller expression or simpler expression instead of the whole elliptic integral. And for that, remember that magnetic field is equal to del cross A. And as I said, we can actually calculate the magnetic field exactly, right? We don't have to go through the simpler approximation. We have a complete expression for that, but we won't do that here. In your homework, you will come across that. Okay, so that's equal to, so let's see what this is. A has a phi and a magnitude there, right? So let me process this a little. So del cross with, there are two pieces in A. There is a direction phi hat, and there is a magnitude of A, which depends on rho and z alone. It does not depend on the angle part of it. The angle is completely in the direction. So this is equal to, I can either get the first one or the second one, right? So this is del cross phi times A, like the magnitude of A, plus I can, oh, actually we can use the, yeah, let's not do it this way. Let me try to motivate you to do the, I think I've noticed that you guys try to like the determinant process better, right? So remember the determinant equation is for the cross product is 1 over H1, H2, H3 times H1 times, in this case, rho hat h2 times phi hat times h3 times z hat, and then you do d by d rho, d by d phi, and d by dz. And here you do the component A rho with an h1, component A phi with an h2, and component A z, right? Component of the vector in the z direction times 3. What is h1, h2, h3? I can write here maybe, right? h1, what is h1, h2, h3 by the way? Anyone? For cylindrical coordinates that we're working on?
H1 1 and then H2 is 1 over rho, and H3 is 1 over rho squared.
No, 1 again. That is for spherical coordinates that we'll be talking about. And it is not 1 over rho, it is rho here, and this is 1. Okay, so how do you see that? Remember your d length square in cylindrical coordinates is d rho square plus d phi square times rho square plus dz square. Correct? So that's your h1 square, which is 1. That's your h2 square, which is h2 is rho, and that's 3. If you want to think of it from differential point of view, then the gradient is equal to rho hat times d by d rho plus phi hat times 1 over rho times d by d phi, and that is z hat times d by dz. This expression you can get from anywhere in a handbook or something, and these quantities that sit in front, that's your h1. There is 1 here, and rho there, right? So that's your h1, h2, h3. That's your h1 square, h2 square, h3 square. So various ways. So that's the length of your, like if you were to take a cylinder and make an infinite small element, that's the arc length that contributes that. Like arc length of a circle as a radius times the angle, right? That's what that is showing up. Any questions there? Okay. Should I elaborate on that? Okay, so yeah, so if I were to use that in here, so h1, h2, h3 is 1 over rho. So this is equal to 1 over rho. So and up there that's 1 times rho hat. So forget the 1. h2 is rho times phi hat, and h3 is just z hat. Okay. This is d by d rho, d by d phi, that stays the same, and that's d by dz. Here now, notice the vector A has only a phi hat component. It doesn't have a z hat component. It doesn't have a rho hat component. So that means 2 of the component is 0. So it has only in the phi hat direction, that's this. Right? That's this piece. These 2 are 0, even one without h1 and h2. So that's 0. That's 0 because our vector we have said is in the phi hat direction. Right? And your A is whatever that expression is, we'll keep it as it is. That's your A. But we shouldn't forget our h2. h2 is rho. Okay. Is that clear? And from that point on, you just take the determinant. Okay. That is how you use this expression. I often do this mechanically. I just expand this out, get this at each basis. But I've noticed that when you're beginning to take curl, this is sometimes easier to use. Okay, so let's see what this is equal to. We have rho hat times d by d phi of 0, d by dz of A, right? So that's one piece in there, and there is a rho hat, and this cancels out, right? So this is rho hat times this cancels, and there's a minus rho hat, and d by dz of A, the rho and rho cancels out. So the z derivative with respect to the magnitude of A, that's contributing in the radial, cylindrical radial direction. What about phi hat? It doesn't contribute because this of 0 and that of 0, that is not there. And finally z hat. So that's plus z hat, plus z hat. And in the z hat direction, you take a derivative. Yeah. Z hat direction, this operates, so there's a 1 over rho times derivative by the rho of rho times A. So this can operate either on a rho or on the A. So we have minus rho hat. Take that, find the derivative with respect to z, and z hat has two pieces in it. If I hit the rho, that then I have 1 over rho times A, and if I hit the A, the rho cancels out, so it is just the derivative of A with respect to rho. That's your expression, and let's calculate that, and hopefully we'll have time to interpret that also. So derivatives are easy. You can now do that. Any questions at this stage, by the way? Okay, so A, remember, is as a magnitude is equal to, so this is the magnitude of the vector potential. So that was equal to mu naught over 4 pi times I pi A square times rho over z square plus rho plus A the whole square, 3 by 2. We have to take the derivative with respect to z first. So this is dA by dz. That's equal to, so that's the only place where it hits, right? When you're taking the derivative with z, that's the only place. So that's mu naught over 4 pi. And when I take the derivative, so there's a minus 3 over 2. I pi is square times rho divided by, this becomes pi by 2, right? Rho plus A square pi by 2. But then we have to hit the argument also with respect to z, so that's 2 times z. Okay. So that's equal to, that's pretty much 2 cancels out. So there's a 3 rho z, right? So I like this as minus of mu naught over 4 pi times, let me keep the I pi A square intact. And I have 3 rho z divided by z square plus rho plus A the whole square, pi by 2. And accordingly, that's what is going to be in the rho hat direction. That's our rho hat component, if you want. And the negative sign, already there was a negative sign that we derived just now, so that will cancel that out. Let's do the derivative with rho also. So that's equal to, but now it can hit 2 places, right? It can either be here or there, so there are 2 places it can hit. So the first, the dA by d rho, so that's mu naught over 4 pi. So when it hits the numerator, it's simply dividing out by rho, right? So I'll just write this as A over rho. Like one of the pieces is simply A over rho. Correct? And the second piece is when I hit the rho here, it is equal to plus mu naught over 4 pi times minus 3 by 2 I pi a squared, and rho stays as it is. And when I differentiate the denominator argument, basically that's rho plus a that comes out, and divided by z squared plus rho plus a the whole square pi by 2. The factor of 2 cancels again like earlier, and there is a minus 3 that shows up. So but the z component has a plus rho, right, plus dA by d rho. That was our what we said was the z component, which gives you, I'll add this up, so it is 2 times that quantity in here. So it is 2 times a over rho. So that's so it is mu naught over 4 pi pi a square. And this is when I divide that rho, that's gone there. But what I'm going to do is that this is z squared plus rho plus a the whole square, 3 by 2. But I can multiply this out with a one more factor in here, so that's 5 by 2. So that's z squared plus rho plus a the whole square. And the other piece, which I write it as mu naught over 4 pi. Like we won't use it so much, but it's good to at least see the direction of this. What's this plus and minuses? Meaning we do very little analysis of this. This b rho 3 rho plus a. Z squared plus rho plus a the whole square times 5 by 2. So should I simplify this further? Let's see. Three rho square. Yeah, let's keep it as it is. I think it's okay. Right. So let me proceed and see what this means. Like time and oops, I should keep the other one in right. Okay, so what's my vector potential, magnetic field then is equal to, that is a minus rho hat piece there, so it's minus and minus is plus, so that's plus rho hat, right, which is mu naught over 4 pi times the magnetic moment if you want, so that's pi a square times 3 rho z. It's a positive quantity, that's a simple thing I want to keep for a moment. And there is a z hat component plus z hat, which is given by this whole sum. So it's mu naught over 4 pi, and and if rho is really small, so there is always a z square, so it will always be positive, right? So if rho is 0, so then this will go away. If you're very close, I mean, because you want to set it to, you don't want to set it to 0. If this is really small, that can be, that will not be, so it will always be positive, that's what I mean. So that's pi a square. And let me write this as z square plus rho plus a square. And if you want, minus 3 rho times a. But if this is within the limit of k square less than 1, this will be positive. divided by z square plus rho plus a. And I want to give a small interpretation of this. So what's this mean? Remember, this is the magnetic field due to a circular wire. Circular wire acts like a magnet, right? So we are having this circular wire here. That's your axis. That's your current I. And we are close to the axis. Our magnetic field will be like this. That's our magnetic field. That's your B, and it will be like this and keep going. But take a point very close to the axis, magnetic field line. If you're right on the axis, it is with respect to the axis. Otherwise, it makes a small angle, very tiny angle. That's your magnetic field, B. See the directions of the magnetic field. It has a radial component and it has a z hat component. This is usually small, so that's your rho hat and that's your z hat. This magnetic field in the direction of rho hat is this piece here. In the direction of z hat, that's that piece there. And of course, notice if you set rho equal to 0, this goes away, the radial component goes away. Most of this also goes away, but this piece survives. So the magnetic field in the limit, like so if you set rho equal to 0 exactly, which we already know, right? We have done that, like we do this very early in physics, that then all this goes away. If you're right on the axis, everything goes away and you're left with just this piece. So that's mu naught over 4 pi times I times pi a square times that is z square over rho is 0, so that's z square plus a square times pi by 2. Okay, which we saw long ago, but that gives you a feel for how this all works. In your homework, I have done most of this using the vector potential. You have to repeat this, some of it in your homework, and you have to do this for the magnetic field also. That will be the small challenge. I give you the expression for the magnetic field, and you have to do this approximation, the leading order terms you have to keep and capture the leading term. It's a little, if you're not careful, you may not get it. So try to be careful and make sure you keep all the terms to the k. What I suggest is that keep all the terms to k raised to 4, even if it is a little extra work. So just keep all of them to k raised to 4 and you cannot make a mistake then. Okay. Okay, I'll stop here. That's all.
Have a good weekend.
Yeah, you too. Enjoy.
Yeah, I will talk to you.
Christian, do you have a few minutes or you're ready to run?
I got to go to the Elks as soon as I can, but I can talk for a couple minutes.
Just a few minutes. I just want to fix a time and all that. Yeah, let me end the.
Have a good day.
I want to. Oh, hi. Bye, Bowden. Yeah. I want.